Right, good morning, engineering students. We've looked at the nomenclature of the functional groups from alkenes, alkynes, benzene compounds, which you are going to, which are known by the common name of aromatic compounds, alkyl halides, alcohols, ethers, aldehydes, ketones, amines, and then lastly carboxylic acids. So in a short while we are going to be looking at the naming, how to name structures, organic structures that may contain more than one functional group. So far we've only been looking at the organic compounds having alkyl groups like methyl, ethyl, propyl, butyl as the substituents. But that's not the reality. You're going to see, for example, you can have an alkene. It can have something like a halogen, or it can have an OH group, something like that. When I'm talking about something like an alcohol group, you're going to come up with those rules. But in the meantime, in trying to name those structures, those organic structures that contain more than one functional group, we're going to be focusing mostly on the bond line structures, these line structures. So this short video is meant just to give you a revision of how to convert the normal Lewis structure. This one containing carbon and hydrogens are being shown here and there into the simplified. It's like the shorthand notation, this bond line structure, so that afterwards we're going to be focusing on the bond line structure as opposed to this normal chemical structure. So this small presentation is only meant to show you how we can convert just the normal structures into the bond line structures. And to show that one, I've just chosen a few structures like the first one, which perhaps I can put a letter. There is A, there is B, and then there is C, there is D, this is structure E, and then there is structure F. Yeah. So there is A, B, C, D, E, and F. 6 structures. Okay. 1, 2, 3. Okay. So okay, the first one contains a double bond. The second one contains a triple bond. This one contains a benzene. This one is an aldehyde. This is a ketone, and this is a carboxylic acid. So let us just try to see how the first structure converts to the bond line structure. Yeah, I believe you can be able to see the bond well. A CH3, that's our CH3. Then here there's a double bond, and then there is stoichiochemistry. So in the bond line structure, if there is a hydrogen is not normally shown, but other atoms are shown. So for example, there is the chlorine, is going to be shown as there is the chlorine. And please note here, the hydrogen and the chlorine are opposite sides of the bond. Then after that one, the carbon here, you see where there is the hydrogen and this bond is down. So here there is hydrogen and this bond is down. So this has CH2, this has CH2. Then there is a carbon with a hydrogen. So this is a CH3, this is another CH3. Yeah. So this structure A converts to this structure. I believe it can be seen well on the board. Okay. The second one here. Now, they are moving like this one doesn't mean that's how we're going to number, but in general we're going to number because this side is going to be closer to the double bond. So this is likely to be numbered, but that is not the aim now. You're not going to be naming, you're not going to say this number 1, whatever, but the aim is to show how this structure translates to the bond line structure. So let's see. There's a CH3, there's a CH3, there's another CH3. Have you seen how it's been drawn? So there is a carbon here, there is a CH3, so there is a CH3, there is a CH3, there's a CH3. Then there is a carbon with a, that's a triple bond. Can you see how the triple bond looks like on the bond structure? There's a, what you need to know, when you have a triple bond, please do not draw a triple bond like this, yeah? That is wrong, yeah? So when there is the triple bond, you must show it linear. So this part is linear. Then there is a carbon with a CH2, so you can see how it moves. Then there is a carbon here, there is a CH3, yeah? There is a CH2 here, and then there is a CH3. Then coming back here once again to this carbon, there is a CH2, and then there is a CH3. All right? So this structure translates to that bond structure. Now for benzene, okay, you can see well. Okay, good. So as usual, the hydrogens are not normally shown, and the carbons, you're just going to show them as the line. So in this case, this one has got 1, 2, 3 bonds. 1, 2, 3. So the hydrogen is implied. It's not shown here. This carbon has got 1, 2, 3. So the hydrogen is not shown here. This one has 1, 2, 3. The fourth bond has got the bromine. This carbon has got 1, 2, 3. For the fourth one is that bond which is protruding. There's a carbon with a hydrogen. This is 6 and 6. So let's see. That is that carbon. That is that carbon. This is that carbon. That is that carbon. This is the carbon with the bromine. Then there is the carbon here, CH. There's a CH3, and then there's a CH3. Are we together? Good. Structure D. Okay, so there's a carbon with a double bond. That's a carbonyl group, and a hydrogen. So this is an aldehyde. Now I've been able to draw it either up or down, but it doesn't really matter. But the issue is, the reason why I've drawn it like this is, okay, perhaps I should have made it like how, perhaps that may be a bit, okay, so this is like saying, okay, let me just try to see what I can draw it like this. First of all, so that it's going to make sense. So there is the aldehyde group, there's the CH2, then there is the carbon with the double bond. There's the hydrogen down and the hydrogen up. So the hydrogens are trans, yeah? That's a trans double bond. Then there is a CH2, there's a CH2, then there's a CH2 containing the chloride group, yeah? But usually, when you draw a structure like this one, like drawing this up and down, you know it's not good. It's usually good to draw zigzag. So that's why, if I'm going to redraw this structure, I can redraw it down and then I put my aldehyde like this, yeah? That is the normal way of drawing your zigzag structure. Though this one I'm drawing it straight, but it's best to draw it up, down like that, yeah? Zigzag structure, yeah? Okay? So this bond line structure is equivalent to this Lewis structure. The Lewis structure, as you know, I've not yet put those, but where atoms contain lone pairs like this one, you need to show, yeah? Like in this case, I put 2 lone pairs. The chlorine has got 3 lone pairs. Which other atom did I put here? This chlorine has got 3 lone pairs. Something like that, yeah? That is the Lewis structure for that, yeah? Alright? So that is structure B. Let us look at structure E. Okay, so there is, okay, let me see. Okay, so this is a CH3. So there is the carbon with the CH3. Is it really, I'm just trying to see whether, okay, good. I think it's the same. Okay, it's the same. I thought I had misrepresented. Okay. So this carbon with the bromine is this carbon. So there's the carbon with the bromine, and next to it there is the CH3, and then there is another. This CH3 is that CH3, yeah. Okay, good. So that is CH3. So there are two CH3s, and then there is the carbon with the bromine. Next to it there is the carbonyl. So it means that this is a ketone, because the ketone, it means that there is a carbon with the double bond with the carbonyl group, and it's next to a carbon and a carbon. There is no hydrogen next to the carbonyl group. So it's a ketone, and then next to it there is a carbon with a CH3. It means that there is a hydrogen which is implied here. Then there is a CH2, and that CH2 contains an OH. Yeah? Okay. Then the last structure here. This is a what? This is a carboxylic acid. There is a carbonyl group plus the OH. So in the bond line is just being shown like this one, the carbonyl group. The carbon here is implied. So I'm just going to show a double bond, and then I put an oxygen here. So that is this is a carboxylic acid. Then there is a carbon with a CH3. Can you see here so there is a CH2, which is that CH2. Then there is an important presentation here. In this case, the two hydrogens are on the same side. So this implies a hydrogen and a hydrogen on the same side of the double bond. It means that the hydrogens are cis. Can you see they are down here? So this can also be shown as that bond is actually going up, because the bond angles are usually 120 degrees, yeah? So this carbon is that carbon, then there is a carbon with a CH3, and then there's a carbon with a hydrogen, yeah? Alright? So this is the structure, which is this is the bond line structure for this structure here. So what you're going to be doing next will be to use these bond line structures to try to come up with the rules on, for example, like in this structure, it's got a carbonyl, it's got a ketone group, it's got a halogen, it's got methyl groups, and then it's got an OH. So in that case, which is the main functional group, yeah? And then if there is the main functional group, then the others are going to be substituted. So for example, if you're going to have something like a ketone, if it's going to be the main function group, what will be the name? If for example the alcohol in this case is going to be like the main group or the substituent, what will be the name which you're going to give to that? We're going to come up with those rules, yeah? Yeah, so we'll come up with all those rules, and then we'll see how we can name general organic structures that may represent the compounds that you're likely to get in real life. So I believe you've really enjoyed the translation from these Lewis structures to the bond line structures. Yeah? Thank you very much. Yeah? Okay.